Okay, so let's just carry on where we were. We just have like one more 5-minute derivation to do for the other fundamental equation. So the divergence of B was equal to 0, no monopole condition. Let's now do the the curl of the field. Oh, sorry. All right, so now we're going to compute the curl of B directly from Biot-Savart. All right, so how does this go? We just have, once again, the same starting point, but now with curl. Curl of B at R is equal to mu0 over 4 pi. Now I've got my volume integral over my source currents of now the curl applied to the expression that I had in my Biot-Savart, which was just current density, R prime cross R minus R prime divided by R minus R prime cubed. All right, so we can just use the same trick as before to replace this thing with minus the gradient of 1 over R. But let's do this. So as above, but using another identity. Okay, and this identity looks much less friendly because it's an identity for the curl of the cross product between two vectors. So what is that? Again, just a fact that you can prove for yourselves on a Friday night when you don't know what to do. B dotted into div applied to A minus A dotted into div applied to B, okay, and then plus A times div B minus B times div A. Okay, so these are just like boring manipulations that you have to make. So so again, typically these do not require like super high conceptual capabilities for this. This is really like mechanics. You kind of apply that thing. If you develop a very, very good intuitive picture of this particular identity, then please let me know, because as far as I'm concerned, I kind of I have a way of thinking about it, but it's not completely foolproof. So anyway, just to say, yeah, this is not the kind of thing I would put in an exam. Okay. Anyway, you've heard it. Okay, so what do we do? Let's just brute force the calculation of this integrand that we have here. So we have the curl of this whole thing, j of r prime. And now I'm immediately going to use the thing that we had, that this thing was minus the gradient. I'll put a minus sign here, and I'll just do the cross product with the gradient of 1 over r minus r prime. Okay, so this thing here with the minus sign is equal to this integrand here, right? Okay, so that's when things get fun, because once again we have here a function that depends only on r prime. It does not depend on r. Therefore, any differential with respect to any unprimed coordinates acts trivially on this. It just gives 0. Okay, so lots of terms cancel. So let me call this one A and this one B. Okay, so each time I have a gradient applied, each time I have this operator here applied on A, I get 0. So if I look at this first term here, this would be this operator applied on A, but A, being this one, does not depend on unprimed coordinates. Therefore, this thing is 0. Okay? Then I have this term here. So what is this term here? So I've got the A, which is, this one here, maybe with a minus sign. So what do I get? first contribution is just j as a vector of r prime, okay, dotted into this operator. All of this applied onto B, which was the gradient of this thing. So that's the first non-zero contribution. And you see again, just jumping, this one here again has the differential operator acting on A being this R prime dependency. So this term here is also 0. So I only have this one left. Okay? And this one here, when I just rewrite it, this. So I just have minus the J at R prime. With now the divergence of the gradient of 1 over r minus r prime. Okay, these are the only two terms that do not vanish. Okay. Now, we have a fabulous identity, which is somewhere buried in chapter 1, but this one is almost worth knowing by heart. So it's equation 1.64, which tells us that the Laplacian of 1 over r is just minus 4 pi the delta function in 3D of r minus r prime. Okay, so this is an identity that's in the very first chapter. It's just something that you can invoke in this case here. So the last term, you see the last term here, I've got the divergence of the gradient, so just the Laplacian acting on 1 over r, but this is just minus 4 pi delta. So you see this thing here becomes just 4 pi delta of r minus r prime times the j. Okay, and here just to confuse you, I'll write j at the point r. Okay, this is the vector notation here. Okay, so you understand why I can replace the argument of j as r instead of r prime. Or you don't. Huh? Because of the delta function. So the only point at which this thing is non-zero is the point at which r is equal to r prime. Therefore, anything touching the delta function like this, I can do whatever I want, be it r or r prime. It's the same thing. Okay, so that's what the last term is like. And this one. So you see, when I take the integral now, mu 0 over 4 pi, integral over my volume d tau prime of this thing here, yeah, then what is this? You see the 4 pi goes, I just get mu 0 with j at point r. Okay? You can take it if it's important. Okay, so that's just a very simple simple thing. Now we just need to treat the other term. And here we have a tiny bit more work to do, but it's still not too bad. So what's this other term? I just have the current at r prime. Yeah, this one here, right, dotted into the gradient like this times the gradient of 1 over r minus r prime. Okay, so this whole operator here applied on this thing here. Well, so what can I do? You see this, everything here is a function of r minus r prime. So what I can say is actually when I take the differential here, instead of taking the differential with respect to r, I'm going to take the differential with respect to r prime. But then, you know, the reduced argument is r minus r prime, so I pick up a minus sign. So what I can do is say, actually this is just like minus j at r prime dotted into the operator nabla with the primed coordinates times the gradient of 1 over r minus r prime. Okay, just like basic differential identity that I have. All right, so what do I get in the integral? I've got minus mu 0 over 4 pi, integral over my volume, d tau prime, of this whole thing here. So I've got j at r prime dotted into the gradient prime with the gradient unprimed over r minus r prime. All right, so that's an integral, but now I can do the following tricks. So trick here. We want to do a partial integral using, kind of annoying this magnification, using the identity that if I take the divergence of some function times some vector like this, some vector field, this is just f times the divergence of a plus a dotted into the gradient of f. Okay, so you see what I'm going to do here is kind of inverse this thing, right? So now a is going to be this this one here, okay, and this term here is going to be this term. So you see the f is 1 over r minus r prime. The a is just the j of r prime here. And now what I do is I say the integral of this thing here is equal to the integral of this minus the integral of this. Okay? So the integral is equal to now minus mu 0 over 4 pi. And now I've got the integral over my volume, d tau prime, of the divergence of f times a, right? So this is really just j of r prime divided by r minus r prime. Okay? And now I've got this term on the other side, so plus mu 0 over 4 pi. And now the integral over my volume, d tau prime, of this term here. So this is now just in the primed coordinates. Actually, yeah, this is a prime coordinate, of course. Yeah. So in the prime coordinates, essentially what I get is just the div prime of j of r prime divided by r minus r prime. Okay, so this is just like a simple manipulation with this partial integral with this simple vector identity. Okay, now this thing here okay, so if we integrate over all space, I mean, we can rewrite this using the div theorem. Becomes just a surface integral. and we put this surface to infinity, namely we integrate everywhere, and we assume that J of goes to 0 at infinity. So this first term is just equal to 0. So this first term vanishes. Okay, I just bring my volume into a region where my source currents are vanishing, if you want. That's another way of seeing it. Okay? Right. Now, for the last term, well, we assumed essentially a steady state. So the divergence of my source currents is equal to 0 anyway. All right, so once again, we've got this glorious representation of a big fat 0, okay, which is cool. So now just collecting terms, collecting all terms. We get simply that the curl of B is equal to mu 0 times the local current density. And this is known as Ampere's law. And again, a nice little box around this equation here. Okay? So here, the way I've presented it, which is not the only way to do it, is really to start from the explicit expression from Biot-Savart and just compute what the divergence and the curl of the magnetic field are, and you just see what it is. So the curl of B is just the local current density modulated by this mu 0 constant that we have there. Okay. So of course this is in a differential form, right? Okay, so we can just do a little extra manipulation. So if we use if we now invoke Stokes' theorem, what can we do? Well, we can simply integrate this curl of B over a certain surface that we have. So you do such an integral here. And what that means is that this becomes the line integral over the path enclosing this surface of B dotted into the displacement along this curve. And what would this be? This would just be mu 0 times the integral over the surface of the current density dotted into dA. Okay, so then we just get the integral form of Ampere's law. So the integral over a path of B dot dl is equal to mu 0 times the enclosed current. Okay, and this I enclosed is just the integral over the surface. Let me write it this way: dA dotted into J. Okay, so again, these are this is ampere again, but now in integral form. Okay, so you see, similarly to Gauss's law, these laws give us an easy way of computing what the magnetic field is if our problem has a certain amount of symmetry associated to it. Okay, so so only if we have such very drastic simplifications of exactly mathematically symmetric situations can we greatly simplify our lives in our calculations. Okay, so yeah, so super simple example. So super simple example. It's the example 5.5 of an infinite wire now. Wire. Okay, so what do? I've got my my wire here. The wire carries a current I. Okay, and the what I expect is that the B field is going to be circumferential like this. Okay, so so to compute the value of B, well, so the field itself, B is going to be some amplitude with the kind of phi hat vector. So phi hat is just a unit vector going around these polar coordinates in this plane. So what do I get? I get so the integral of B dot dl over the path P. So my path P, what is it? It's just like a circle. So that's my path P. It's a circle at a certain radius. Call it S, like this. So what is this? This is just the value of B times 2 pi S. And this has to be equal to mu 0 times the enclosed current. The total enclosed current is just I. Okay? So therefore my field is just mu 0 I over 2 pi S with the phi hat. Okay? And it's as simple as that. Of course, if my thing is asymmetric, that is, if my wire does a kink or starts moving strangely, then I cannot use that. I have to go back to Biot-Savart. So Biot-Savart is like the super robust, always valid version of this, but Ampere is just like the nifty trick to do it very, very easily. Okay, so so those are simple things. Now, in the yeah, essentially what I would like you to do, so for a self-study or reminders of things that you've already calculated, so check out examples. So there's the example 5.8, which is of surface current. Oh, that's cool. On an infinite plane. And yeah, I mean, I think these three are fun. So 5.9, it's the classical example of the solenoid, where you have to show that the field inside is non-vanishing, but outside it's vanishing. And then 5.10 is the toroidal coil. That's also cool. That's interesting. There's some bloke who computed an algorithm to recognize coil into. Okay, so so these are like very simple examples of applications of Ampere's law that that I'll let you look at because it's quite straightforward, and you can be absolutely assured that at the exam there will be a question on Ampere's law that you'll be able to use it. Okay, so it's highly recommended that you you study these examples. Okay. Because I expect you to be able to use Ampere's law without too many hiccups. Okay? So that's the kind of theory. Okay. How comfortable are you with Ampere's law? I mean, you did basic examples with it, I guess, in the first course, no? So, yeah? Or am I kind of assuming too much? No? No? Well, okay. So, okay. Anyway, if you look at these three examples, you'll be in a very, very good position for the midterm at least. Yeah. Okay. Now, you know, again, time is going fast. Let me just maybe mention a few little things. Also, in preparation for discussions that we'll do in much more detail after the midterm, when we go back to dynamics, we'll be playing with these representations quite a lot. But okay, so let's just carry on this. So next thing I want to mention are things about the vector potential. Okay. So you remember in electrostatics, we could write the electrical field as minus the gradient of some scalar field. In the case of the magnetic field, since the divergence of B is equal to 0, we can always write that the B field is obtained as the curl of some other source field, which is the vector potential here. Okay, and the statement here that we can do this comes from Mr. Helmholtz. Okay, it's Helmholtz theorem, which is also in the in chapter 1. It's just a statement. So if you have something that is divergenceless, then you can always view it as the curl of something else, the kind of circulation of some other object that has that. And then by simply using this representation here, you guarantee that this is going to be the case, because we know that the curl of this thing is just going to be 0. Okay. So what can we do? We can connect this with Ampere's law. So if we try to do a connection with Ampere, then what do? Well, we're going to compute the curl of B, which is the curl of the curl of A. But you see, this looks dangerously like the identities that we've used just before, right? Except that now one of the objects is this differential operator there. But nonetheless, we can just do this. And then you can write an identity that this becomes the gradient of the divergence of A minus the Laplacian of A. Okay? And this thing, we know from Ampere that it has to be mu0 times the current density J. Okay. Now, there exists an ambiguity in defining A. And this ambiguity is resolved by what we call a gauge choice. So what do we mean by this? Okay. Well, best is to do an example. Okay. We can choose to set that the divergence of the vector potential is equal to 0, just by choice, without essentially limiting our representation in any way. Okay, so why is that the case? Why? So, so start with an A0 having non-zero divergence. Okay. We will let another vector potential, we'll call A, be equal to this A0 plus the gradient of some function to be determined. Some to be determined function. All right, so why does this this work? Well, first of all, if we have the divergence of A, this is now the divergence of A0, okay, plus just the Laplacian of this extra function lambda that we have, okay? So requiring div A is equal to 0 means that essentially we get an equation telling us that the Laplacian of this auxiliary function lambda is just equal to minus the divergence of the A0 that we had before. But you recognize this equation. This is really just like a Poisson equation. Okay? So this is Poisson-like. That's a fish. Huh? Okay? So it's a Poisson-like equation that allows you to determine this function lambda, because now the divergence of this thing is just some source function. So it looks a bit like you're computing electrostatic potential knowing some charge distribution. It's the same equation. Okay? So you can just write down the solution directly. Okay? So provided this A0 goes to 0 at infinity sufficiently fast, what we can do is just use the solution of the Poisson equation that we had seen in electrostatics to immediately write what this lambda of R is. This lambda of R is just the kind of, you remember Green's theorem, all these things. So integral d tau prime over your space of now just your source function, right? And the source function, of course, now it's in prime coordinates because I'm doing this this integral here, A0 of R prime, all that divided by R minus R prime, and you're done. Okay, so so that's just like one one thing. So if you want again a proof of this, so apply the Laplacian, and then you can just use that the Laplacian of 1 over r minus r prime is just, once again, minus 4 pi the 3D delta function of r minus r prime. Okay, and you see then you get it straight in one line that indeed this is a solution to this equation here. Okay, so once you've defined your gauge choice like this, you can always make it work. The reason why it works, of course, is when I add this particular thing to my vector potential, I don't change the magnetic field. Okay? Yeah, so adding this does not change B, right? Because the curl of a gradient is equal to 0. Okay? It's just a little side note. So I'm free to do that. And that's an example gauge choice. So there are, infinitely many gauge choices that you can make, but that's a particularly convenient one. There will be others in. All right. So so under this gauge choice, Ampere's law becomes the following. So you see, I just with my original identity, I want to just rewrite my. You see, I want to use this thing here, right? So the curl of B is now this, but now I've chosen that the divergence of A is 0. So really, the curl of A is just minus the Laplacian of A. Therefore, Ampere's law simply becomes that the Laplacian of this vector potential is just minus mu 0 j. So you see we get an incredibly simple equation. So it's like a vector. So vector Poisson, which you have a fish. Sorry, I'm making bad jokes here. Forget about it. No? All right. The solution of this thing is once again very simple because I just need to invert this Laplacian operator. I do that with the trick that we've just seen now and we had already seen in electrostatics. So A of r is just mu 0 over 4 pi. And now I just have the integral over my volume of the source current density, J of r prime, divided by r minus r prime. And again, you can verify that this is a solution to this particular equation by simply using this wonderful, identity that we had with the Dirac delta function. Okay, so that's a kind of very super simple representation of what the vector potential is. And you see the parallel, right, with the electrostatic potential that we had. It's essentially the same equation, but just now in vector form and with a different source term. So here you've got the current density giving you the source for the vector potential, whereas in the original equation for the potential that we had, it was really just the charge density giving us the scalar potential like this. Okay, so that's all, about as economical as you're going to get for the representation of the vector potential. Now, be warned, this is now not a gauge-independent representation. We have made a gauge choice. There are other gauges in which the representations look different for the vector potential. However, the magnetic fields that you would compute are independent of the gauge choice that you will make. Okay, so we'll talk more about gauges later on. I refer also to my earlier discussion about symmetries and conservation laws. The whole point of these gauge choices, they're extremely, powerful, because if you want, you can state that the whole magic of quantum electrodynamics is recognizing that gauge symmetry is a local symmetry, and then you kind of use that idea and you derive all the things you need to derive. But maybe we'll make some crazy comments about that at the end of the course. For now, just view it as being there. Okay, again, so there are some examples in the notes that I'll let you go through. An example of a spherical shell rotating. It's asking you to compute the vector potential for that thing, so that works well. There's also just computing the actual vector potential for the infinite solenoid that was treated before. Again, it's worked out in the notes, so I'll let you have a look at that. Okay, and these are again nice things. So I would say in terms of order of importance, being able to write, a vector potential in a given gauge, it's all very nice, but it's much less important than Ampere's law itself. Yeah, so not knowing Ampere's law is like absolutely unforgivable. Essentially, hesitating about which gauge you should choose, then that's okay. That's kind of on the verge of being above your pay scale. So you can see. So these are like things that are useful, but less useful than others that we've seen. Okay, I mean, I wanted to do like multipoles for the vector potential, but I think that's not going to happen today. So maybe I'll just end with a couple of comments on magnetic boundary conditions. Okay, so you remember all these stories of Gaussian pillboxes and little Amperian loops that we did for the case of electrostatics. Here, it's a little bit similar. So for example, say that we have a surface current. Then essentially, so I imagine I have my plane like this, and there's a certain current surface density, that sigma, that goes like this. Then what I can do is do a little integral of my B dot dA on a certain surface, which looks like a little thing straddling the surface. Okay, so I've got my surface current on this. I'm defining a little surface that kind of intersects this thing, and I'm going to integrate around this loop here, representing the boundary of this surface. If you look at this, so B dl over this little path here, right? So what is this? This is really like the B parallel above minus B parallel below, and by Ampere this has to be equal to mu 0 times this like surface current that I have here. Let me actually, so in the notes I kind of used K as the symbol for this. Let me do this. So this is K, and this is L. So mu 0 times K times L is the total amount of current that goes through this this loop here. So, and this is integrated times L, because I'm just using a constant field integrated over this length here. So essentially what it tells me is that this B parallel above minus B parallel below is just equal to mu 0 times this surface current that I have in there. Okay, so if you rewrite it in full vector glory, then I have that the field above minus the field below is just mu 0 times the surface current dotted into the unit surface vector. Unit normal vector at the surface. Okay, so you get a current there, and you get the field below. So currents like this, normal vectors like this. So then the field goes like that. Okay, so you can work it out with this. Okay, you can write also like boundary conditions for the vector potential. It's the same thing, but now with an extra derivative. But I think I'm just going to leave you to look at the notes for all of this. Okay, so that's the kind of short tour d'horizon of magnetostatics. Next time we'll do. I will make a couple of comments about magnetic dipoles because they're important, and then we'll rush through the matter bit on this, and then we'll move to dynamics. Okay.